This recording is for hydraulic engineering on the 16th of April, 2019. This is class 25 of the semester. First of all, remember that what I announced in class previously was that the quiz 3 that was supposed to be on Tuesday the 16th, that's been postponed until Thursday the 18th of April. On that same day, homework 14 is due, and homework 14 is covering some of the ideas that are included in this lecture, as well as some reference back to the hydraulic jump concepts that we discussed in chapter 13. And then the other big bullet point on your to-do list is the final report for the design project. Hopefully that will be a relatively easy lift for the reason that you've already done the draft submission for phase 1, the draft submission for phase 2 and 3. So you kind of have been working on the project in increments, and it's in this final report that you tie everything together. I'll encourage you to take one last look through the assignment description so that you can get a keener idea of exactly what needs to be in that final report. I've gone to some trouble to give you pretty detailed instructions on what my expectations are. So after you've read through those instructions, if you have any questions, then please feel free to let me know. In the lecture today, we're going to take one last look at underflow gates and another example related to flow underneath a sluice gate. And then we're going to move on to the topic of gradually varied flow. Remember, we distinguish between rapidly varying flow, which is the hydraulic jump, and then those transitions that take a much longer duration or a much longer length in the stream, where the flow is changing in a non-uniform way. So that's gradually varied flow. So first, on the subject of an underflow gate, let's revisit the idea of we have flow going downstream under uniform, steady conditions, and so we have some flow depth. And in the past, we already saw the example of what happens if you put an obstruction in the channel. And you remember that the principle was that if you have an obstruction that doesn't have, where the flow upstream doesn't have sufficient energy to get over that obstruction, then what's going to happen is the flow upstream is going to pool until there's enough energy for it to flow at critical conditions over the obstruction. So this y'1 was the upstream depth after pooling occurred, and what determined how deep that was the amount of energy required. And this minimum specific energy, remember the flow over the obstruction, if we assume a rectangular channel configuration, then the specific energy is 3/2 the critical depth. And so what we would say is that the energy at 1 after pooling is going to be equal to the energy at 2 that's measured on top of the obstruction. So that same kind of idea, looking at the specific energy upstream and downstream of some choke, can also apply when an underflow gate is acting as a choke. And we saw an illustration of that in the lab where we had an underflow gate that was causing the hydraulic jump. And as that gate was lowered, you noticed that the water level increased upstream of the gate. So in this example, the water is flowing from the left towards the right. And the reason why the water level was increasing was so that the pressure at the certain depth that's forcing the water out through that opening, so that the pressure is high enough so that the velocity out through the opening enables equilibrium. Remember, the Q in and Q out is what we call, when Q in and Q out are equal, then that's steady flow, meaning that flow isn't changing over time. And so a sluice gate like this can be used to regulate the flow and measure it. And unlike the broad-crested weir, it doesn't retain sediment, and you can raise and lower the gate to control flow conditions. And so they're pretty useful in hydraulics, and they're used for a lot of different purposes. But what makes them a little bit different than the example I just showed you previously of the other obstruction was in the case of that other obstruction, when there was pooling upstream, it was followed by critical flow downstream. In other words, the energy accumulated upstream until there was just barely enough to provide critical flow over the obstruction. In this case, there isn't critical flow after the choke. The choke is this gate, and the flow conditions downstream aren't governed by it needing to be at the minimum specific energy, but it's governed by the hydraulic structure itself. So we still can use the energy, the specific energy approach, to understanding what is the depth upstream. And so to do that, just to illustrate how we can perform a specific energy analysis on a sluice gate, let's consider some specific numbers here. Let's say that we were able to measure the depth downstream of the gate, and let's say that this is after the contraction, and the measured depth is 0.7 meters. The original flow depth when conditions were steady and uniform was 3.5 meters, and so we know that there's going to be some pooling as a result of that choke. So the question is, how high would the water level have to rise before there's enough specific energy to match up to the conditions downstream? Just to allow for some specific calculations, let's assume that the channel width and the gate width is the same, that they're both 4 meters wide. Let's do these calculations for a flow rate of 36 cubic meters per second. And the original upstream depth before the obstruction was put into place was 3.5 meters. So let's neglect energy losses between 1 and 2. And what we're saying is we want to find out what is the energy required at 2, and is there that same amount of energy available at 1 without pooling? I think we'll find that there isn't. And so therefore, what we're going to look for is there's a certain amount of energy that has to be existing at 2, and so what depth of accumulation upstream is going to cause that energy. So E2 is going to equal E prime 1. So you can pause this recording and try and go through these calculations according to the same process that we've used in the past for specific energy. After just a moment, I'll show the solution here on the screen with the PDF that I've got solving it. But just so you get a chance to try it out yourself, pause the recording, go through the calculations, and see if you can use specific energy to determine what would be the new upstream depth at 1. Okay, so we know the flow rate is 36 cubic meters per second. The channel width is 4 meters. The original upstream depth was 3.5 meters. And after the water goes through that underflow gate, its downstream depth is 0.7 meters. Since it's a rectangular channel, we can calculate the flow per unit width, and so lowercase q, 9 square meters per second. And that is calculated just because it's one way for us to determine what is the energy that's required at location 2. So here at 2, the specific energy is going to be the depth and the velocity head. And of course, there's a number of ways for us to calculate the velocity head. We could have determined what is v at location 2 and then done v squared divided by 2g. It can be q squared divided by 2g a squared. Just another way, another approach for calculating the velocity head is flow per unit width squared divided by 2g times y2 squared. Okay, so as you can see, if we do that, then the amount of energy is 9.125. Now, considering that only 0.7 meters of that is in the depth, that gives us a pretty good idea that there's a lot of specific energy tied up in the velocity head here. Now, was there enough energy originally with that original flow depth of 3.5 meters to provide for this? No, because we had the depth of 3.5, and we can find out the velocity head component when we have that same depth of 3.5 meters. There was only 3.84 meters of energy available. And so what we know is that since there wasn't enough energy originally, since the E1 is less than the amount of energy required at 2, then choking will occur. And the water will pool upstream of the choke until the energy that's available at the upstream location after pooling, so that's E'1, until there's that same amount of energy available that is required. So we're saying what would be the depths that could provide that much energy at location 2. So we already know one of the depths. One of the depths that is associated with that much energy is 0.7 meters. So just as we did in previous cases where we were analyzing specific energy, this is going to turn into a cubic equation that we're going to be solving for the roots. There will be one negative root, two positive roots. In this case, we already know one of the positive roots. It's that supercritical root. And so what we're after is the subcritical root that gives us the same amount of specific energy. So the three roots, if you put that into your solver, one of them negative, one of them the original flow depth, and then the other, this 9.075 meters, that is how deeply the water is going to have to pool so that there is enough pressure to push the water out at the velocity that we expect for it to be steady conditions and associated with that, that flow depth of 0.7 meters. So this will be our new depth, 0.9075 meters. Now, of course, in this analysis, we neglected any energy losses, and it would complicate things a little bit further, but I mean, not a lot for us to account for the coefficient of discharge and calculate the energy loss. The approach would be the same. It would change our cubic equation slightly, and the depths would be a little bit different. Essentially what it means is that the pooling is going to have to be even higher than what we calculated, because with losses having to do with the turbulence and the transition, that just means that the water is going to have to pool even more than this ideal theoretical depth if there weren't any losses.
So here are some of the key ideas for the homework assignment. Problem 2 I just thought was a little confusing, maybe the way that it's worded, and so what they're asking for you to find is the dy/dl, and we'll go over today what that is. Problem 3 is closely related to an example we're going to be working in class today, but just to make it perfectly explicit, they're wanting to find out how does the water change relative to horizontal, and so what that means is that you have to find dy/dl and then subtract out the channel slope from that. Now in problem 4, they're asking you to classify a water surface profile type, and we'll talk about what those abbreviations mean as we look at some pictures in class today of what causes gradually varying flow. And so what they're asking you to classify is there are these typical shape designations that are assigned, and so they want to know that in part A. And then in part C, they want to, based on part A, they want you to say, you know, is the critical depth upstream or downstream? Is the normal depth upstream or downstream? You know, sort of like what's at the bounds of the gradually variation, because gradually varying flow doesn't vary forever. It eventually matches up with some sort of uniform flow, and so it's asking, you know, where are the controlling depths, and you know which one is upstream and which one is downstream. And then one assumption that you need to make in order to do problem 25 is the coefficient of contraction. And so that's an underflow gate problem where you should use a coefficient of contraction of 0.6. All right, so if you didn't get all those written down, it'll be in the video. We have to keep moving. Let's talk about gradually varying flow. Now, I've got a picture of a river here, and most of the time the flow will be varying in some way. When we talk about a natural channel, it would be very unusual for us to have any length of channel that is uniform flow unless it's an engineered channel, you know, like a canal that's prismatic with the uniform slope. But far more commonly, we have creeks that are changing their profile, they have variation in slopes, there are obstacles in the way, and all of those things affect changes in the velocity, in the depth, the channel width. Here in this picture, you can see that the width is narrow at one section, it's wide at another. And so over the coming couple of weeks, what we're going to be doing is looking at the numerical methods you need to find out what is the depth and what is the velocity, or what is the water slope, when you have these real-world changes in channel width and depth and slope and so on. So there's lots of things that can cause these irregularities, but by gradually varying flow, what we mean is anything other than a hydraulic jump or water flowing over the edge of a waterfall. You know, those are the two instances where the depth of flow is varying rapidly. So rapidly varying flow, RVF, is the hydraulic jump where it's increasing its depth really quickly, or if water is approaching a drop-off, then it decreases really rapidly. When the depth changes, the velocity does as well to maintain continuity relationship. Now in the calculations we're going to do, we'll assume the hydrostatic pressure distribution as we go down through the depth of the water. And since the water is open to the atmosphere and is moving relatively slowly in open channels, that's an okay assumption for us to make. It's not so bad. And we are going to be accounting for energy loss. Whereas in the Bellinger momentum equation, that doesn't account for energy loss. Remember, one of the assumptions in the Bellinger momentum equation was that there's a uniform velocity distribution upstream and downstream. And so the gradually varying flow approaches that we're going to work through kind of do account for the energy loss. So let's look at some pictures. Here is gradually varying flow as water approaches a choke of an underflow gate. And the reason why the depth is increasing is so that enough energy can accumulate upstream of the gate to force the water under the gate at a high velocity. It's looking for in to equal out. And initially, when that gate is dropped, there isn't enough energy to push the water under that gate at a high velocity. And so it begins to pool until finally there is enough energy upstream of the gate so that in equals out and it comes into equilibrium. But this section GVF is the gradually varying flow. Any guesses on what UF stands for? Lots of good guesses. You're right, uniform flow. All right, so here is water that's approaching a drop-off, and you can see that they've designated that last couple of feet of rapidly varying flow, but it varies gradually as the drawdown occurs as it gets closer and closer to that edge. Another possible cause, probably the most common cause, would just be a change in slope. And here you can see we have a relatively steeper slope matching up with a relatively less steep slope. And so somewhere there's going to be a gradual variation as the two different normal depths have to match. So here's the normal depth for slope 1, the normal depth for slope 2, and you have to kind of connect the dots between those two depths, and it's going to vary gradually. Sometimes the change in depth will be majority after the transition. Sometimes it'll be mostly before the transition. We'll learn how to do those calculations later on. Here's another case of gradually varying flow after the underflow gate. In this case, there's no hydraulic jump. And so what that means is that either this is a steep slope or the gate is open enough that it wasn't causing pooling upstream. But I guess the fact that this is gradually varying argues against that. This is probably a steep slope. So those are some causes of gradually varying flow. Now, the equations that we're going to look at today, the main one's called the process equation, which is, I'm not sure how or why it got that name, but it's pretty serious, the process equation. We're going to be assuming that we have a prismatic channel, which hopefully you remember a prismatic channel is one that can be mirrored along a center line. And so it could be U-shaped, and here's the mirror, or it could be rectangular, it could be trapezoidal or V-shaped, whatever shape, but this normal natural channel would not be prismatic. And so the further we get away from a non-prismatic channel, the worse these equations are at predicting what's actually going to happen. And so sometimes what we have to do is break the channel into sections that themselves are prismatic. And then when we do that, then we can kind of get good results again when we break a non-prismatic channel into segments that are. Now, assumed here is that our bed slopes are relatively small, meaning that we have the channel slope in open channel would very rarely be any greater than 2 or 3%, and as long as we stay below that, then everything's fine. Uniform velocity distribution, this is maybe the biggest weakness in what we're going to be assuming, is that, again, the velocity at the bottom of the channel is the same as the velocity at the top of the channel. And that's primarily where we have errors pop up in predicting what we'll observe in the field versus these equations that we're going to be looking at. And so this error is maximized for shallow slopes, but when you have a relatively deep slope, then the error becomes smaller. Kinetic energy correction factor of equals to 1 means that we're assuming relatively laminar conditions, that the flow isn't turbulent. And no, I'm sorry, the other way around. We assume that the flow is turbulent, not laminar. It was the laminar condition is when we have, for example, in a pipe, when we would have the bullet-shaped velocity distribution is when we would have to have the kinetic energy correction factor of equal to 2. So the kinetic energy correction factor of 1 is saying that our Reynolds number is beyond about 4,000. And that's usually the case, even in a slow-moving stream. Parallel streamlines and hydrostatic pressure distribution, and then we assume that the channel roughness is constant for whatever section we're applying this equation over. That is that you're not going to have a section of concrete with a relatively smooth roughness and then like gravel. You would only be able to apply this over sections where the roughness coefficient is the same. So you'd have to break it up into pieces if it was going to be varying roughness through different sections. Okay, this is a really important drawing, and so we're going to look at this for a couple of minutes and talk about what these variables mean. Okay, I guess the most obvious one to begin with, WS, is water surface. We know that's a free water surface because the little triangle and these ripple marks indicate that it's open to the atmosphere. Now above the water surface, here they've abbreviated it TEL in our book, and that stands for the total energy line, which is the same thing as what we called the energy grade line when we were in fluid mechanics last semester. So the total energy line is this dashed one, and the solid line above it is just for purposes of reference. It's horizontal. It's a horizontal line to show, yeah, from my perspective for a second that didn't look horizontal, but it is. It's horizontal to show how much energy is lost along some length dl. And so H sub f is how much energy is lost. And by the way, when you have uniform conditions, H sub f would equal the slope of the channel multiplied by dl. And so this S naught dl equals HF when you have uniform conditions. But we don't have uniform conditions. And how do we know that this is non-uniform? Anyone? Okay, the slope of the water surface is changing. That's a good way to put it. Go ahead. Very good, yes. So uniform flow, all three slopes would have to be equal to each other. The channel slope would equal the water slope, would equal the energy grade line slope, or the total energy line slope, S sub f. Right, so those three slopes would be equal, so we can see that the water's getting deeper in the direction of flow. How do we know it's getting deeper? Well, over here on the left side is y, our original depth. But then over here, it's y plus dy. And so the water got deeper. So why is the velocity changing? Here there's v and then v plus dv. Does that mean that the velocity is increasing? No. Yeah, the velocity is not increasing, assuming the channel is, the width isn't changing. Here the dv would be negative. because if the water's getting deeper, the velocity would have to be decreasing, assuming a constant width. So here's our velocity head at 1 and 2, upstream and downstream. All right, so we've dug into that a little bit. Just to point out that there is a difference in depth upstream compared to downstream. Yes? No, not necessarily. It may just coincidentally appear that they are. Yeah. Okay, now to give you a bit of background, remember our definition of specific energy. It's that at any location it's going to be the depth and the velocity head. And so starting with the idea of specific energy, and then back from lecture 17, we had the idea introduced that the change in energy with respect to depth is 1 minus the Froude number squared. Now what we're going to do with that is try and predict the slope of the water surface. And what we can do is say, well, the total energy, here in the text it's saying the dH/dl, where h is the total head, including the depth, the velocity head, and some distance above vertical datum, so z. So if you have the slope of the energy grade line being the change in energy with respect to position, so that's S sub f, we're just saying the slope of our energy grade line is how much energy is changing with respect to the distance downstream. And then the slope of the channel, S naught, is dz/dl. And so it's how much elevation is being lost over this length, just channel elevation. So here's what we can do. We can put this into this relationship and predict dy/dl. So that's the change in depth with respect to length. Now we have to be really careful though, because although it looks like the water surface is linear, it's not linear. And so we have to be cautious in applying this dy/dl, because it only applies at a single point. It's the slope at one location. And so just to exaggerate, we've got the water's getting deeper here. Okay, so let's say maybe it's approaching some sort of an obstacle, and that's why it's getting deeper. All right, so it's getting deeper like this. So it's not a straight line, it's curved. And so at any point, right here for example, we could find out what is the slope of the water surface there, but we couldn't simply multiply that slope by some distance, delta L, and then find out what is the depth downstream, because if you project the slope, it's not necessarily going to be the same as the result of that curve. We'll talk more about that in the coming classes. We'll talk about, well, if you can't just directly multiply that by some distance L, then how do you know what the depth upstream or downstream is going to be? So we have to have some ways of integrating this over a distance. And there are some fun spreadsheet ways of doing it. So start bringing your computer again on Thursday, because we're gonna dig into some of those computerized methods. Okay, so this is the general governing equation that's behind all of those methods, and we're just going to look for different ways to integrate it to find out a depth upstream or downstream. You can also use this to find what is the slope of the water surface at a certain point where you know at that location what's the slope of the energy grade line. Now a word about the sign of slopes. In the past, like when we were working with Manning's equation, if the slope was 1% slope, we just put into Manning's equation S equals 0.01. And it was already assumed that water flows downhill. And so we didn't bother putting a negative sign for the slope into Manning's equation. But here we have to be a little bit more careful about slopes. The channel slope is going to be downhill, and so you do need to put a negative sign in here if you want to find the water surface slope. Because dy dl could be positive or it could be negative. Because sometimes the water is getting deeper in the direction of flow, and sometimes the water is getting shallower in the direction of flow. Remember these. And so we may be using the process equation to look at a situation where the depth is increasing, and other cases where the depth is decreasing. And so in the homework assignment, you have a question where you need to be sure that when they tell you the slope of the channel, you make that a negative number. And the example we're going to work today will reinforce that necessity. Okay, so where do you get the slope of the energy grade line? We can solve that using Manning's equation. And for a certain channel, we may know at a location, we can go and measure what is the depth using a yardstick or whatever. We can know the depth in the stream. We can know the roughness, the channel geometry, and so the only unknown in Manning's equation will be the slope of the energy grade line. You physically measure the slope of the water surface, the slope of the channel, and then based on knowing the depth, you can find the Froude number. So if you make that substitution, putting the Manning's equation into S sub f, here's what it looks like for SI units and for the British gravitational. And the reason why that's different is, of course, Manning's equation in SI is Q equals A to the 5/3, S to the 1/2, and P to the 2/3. And so that's SI units, but in traditional units, we have to do 1.486 as the units conversion. That is really terrible. 1.486. And so this is rearranging that to solve for the slope of the energy grade line, what you'd get for SI units or for BG units. Now, this is true regardless of whether the channel is rectangular or trapezoidal, whatever shape you've got. If you have a wide channel, then things become a little bit easier. What you can do if the channel is wide is you can use the normal depth and the critical depth rather than having to directly calculate the slope of the energy grade line and the Froude number. A wide section is one where the width is more than 20 times greater the depth. And what that essentially means, the implication of a wide channel, is that it's so wide that the edge effects can be neglected. Even if it's rectangular, if it's trapezoidal, a wide channel is so wide that the majority of the resistance will be along the bottom of the channel, and whatever resistance you get on the side of the channel can be neglected. That's kind of what we're doing with the wide assumption. So this is the process equation, this dy dl. Sometimes in the book it'll talk about the process equation, and this is the one it means. So the sign of it indicates whether the water's getting deeper or getting shallower. And that's really important at being able to classify the water surface profile into the correct category. And we'll look at some more additional pictures of different physical features that cause gradually varying flow, and we'll show how dy dl can be used as a tool for diagnosing what kind of a water surface profile you've got. One other implication of the wide channel assumption is that the normal depth, there's a simplified way to solve for the normal depth. Normally when we are using Manning's equation and solving for the normal depth, we would, for whatever the shape is, Q equals A to the 5/3, slope to the 1/2, and P to the 2/3. All right, so for whatever the channel is, we would put y into both the A and the wetted perimeter and try and solve for y. But if it's a wide channel, then you can just take the flow per unit width, Q, multiply it by the friction factor, N, and divide by the channel slope to the 1/2 power, and then all of that to the 3/5 power. So these are some simplifications if the channel is wide. All right, so here is an example that we're going to work through. We have a rectangular channel which is carrying 20 cubic meters per second, and it's 40 meters wide and 2 meters deep. And so that does meet the threshold of it's a wide channel. So we can use these shortcuts. What we need to do, here's the bed slope is given, it's 0.00015, and that's downhill. And we have the Manning's roughness N. So we want to find out the rate of flow depth variation. So that is dy dl. And then from that, identify whether the depth is increasing or decreasing. And then finally, find the water surface slope with respect to horizontal. So that means combine the channel slope and dy dl and solve for SW. Okay, so I'm going to pause the recording and circulate around as you're working on this. If you want to check some of your intermediate calculations, I'll be happy to show that to you. So we're calculating the critical depth and the normal depth. And you'll do that a lot over the next couple of weeks because we're always interested in how does the depth at a certain location compare to the critical and how does it compare to the normal depth. Now in the past you already knew what it means when the normal depth is greater than the critical depth, or if the critical depth is more than the normal. Remember that that can tell us if the conditions are supercritical or subcritical. Get into that in just a minute. But so if you substitute in the given depths, the normal depth relative to the depth at our certain location, which is 2, this is just at a certain spot we're trying to find dy dl. And so then the critical depth relative to that depth at that certain spot. That tells us the dy dl is 1.39 times 10 to the minus 4th. Now the interpretation of that is that the flow depth is increasing in the direction of flow. And every 1,000 meters the water depth would be increasing at 0.139 meters. And that's relative to the channel bed so far. It's not until part C that we're finding out relative to horizontal how things are getting different. So the dy dl is just saying, relative to the bottom of the channel, is the depth increasing or decreasing? Now, here on the board and also on the screen, I've drawn some dashed lines to indicate here is the critical depth, here's the normal depth, and then our actual flow depth that we're encountering is above both of those. And this is an M1 profile. That M means mild, and anytime you have the normal depth greater than the critical depth, that's a mild slope. It means that the flow is going to be subcritical. Now, zone 1 is the region that's above the first of these lines. Zone 2 is between them, and zone 3 is from the channel bottom up to the first of the lines. And so sometimes, like if it's a steep slope, then it would be the critical depth that is deeper than the normal depth. But here it's mild. And so our conditions are M1 because the water surface itself is in zone 1 up here, and M mild because the normal depth is greater than critical. So there's like a lot of reasoning that you need to be sure to include in your assignments and in the exam, the final exam. You'll need to, explain, not just it is M1, but show that you know the rationale for why it's an M1. So
So if the depth was y equals 0.8, would it be M2?
it would be M2, yes. If the depth was 0.8, then it would be M2. All right, so now part C here. So we've got some dy dl that we calculated, and then this is where we need to be sure that we account for the negative sign of the slope. So the water surface is going to be, actually, it's getting deeper, but the downhill slope is steeper than the rate that it's getting deeper. So the net effect is that it's actually losing, the water surface is losing elevation in the direction of flow relative to horizontal. So my sketch doesn't really show that because we've just got, here's the channel bottom, but what it means is if we were keeping track of, it's getting deeper in the direction of flow, but it's getting deeper more slowly than we're losing elevation in the channel bottom. So like the absolute elevation of the water is decreasing. I guess that's why it's flowing from left to right. You can actually have an adverse slope. Sometimes the water flows uphill. Anybody ever been to a water park where you actually went uphill? I have. It's great. Had a ball. Abu Dhabi. Yeah. Water flows uphill when you've got enough money. Yeah. Yeah. All right. Any questions on this example? All right. So remember, there are three important depths that we're going to be using to classify a water surface profile. The normal depth, the critical, and then whatever is the given depth at a certain location that's been measured and reported in the problem statement. And designating whether it's M1, M2, M3, those sorts of classifications can be helpful to try and figure out what's causing the observed behavior. So even if you don't know what's downstream, the simple fact that you have an M1 profile would tell you there's probably an obstruction downstream that's causing pooling where you're at. And it also helps you to predict as you continue in a certain direction whether it's going to be getting deeper or shallower. So a mild slope is any time the normal depth is greater than the critical depth. And steep is the reverse of that. When you have the normal depth less than the critical depth, that's indication of steep. Of course, critical is when they're equal. Horizontal is when there's no slope. And then here's an adverse slope where the water is forced to flow uphill briefly. Now just the variable definitions sometimes can be confusing. Here they're using y naught to mean normal depth, and previously we've sometimes called that y sub n. But the critical depth, fortunately, that doesn't change. But what you need to do to classify whether you have, your first one is M, S, C, H, or A, is just comparing the normal depth to the critical depth. And so, when I say explain the logic behind your water surface profile designation, the first thing is just comparing those. Then the next step is the zone that you're in. Zone 1 is above the highest line. And by the way, sometimes the highest line will be the normal depth, and sometimes the highest line will be the critical depth. But it's still, regardless of which one's on top and which one's on bottom, it still divides this region up into three zones: Zone 1, Zone 2, and Zone 3. Okay, Zone 1 is above the normal depth and critical. In this case, if it's a mild slope, then the normal depth would be on top. Zone 2 is between them, and then Zone 3 is below both of them. All right. So if the dy dl is positive, then that means that the depth is increasing relative to the channel bottom. Dy dl negative means that the water depth is decreasing in the direction of flow. Dy dl of 0 just means that you have uniform flow. That is, the depth isn't changing in the direction of flow. And then if you had a free overfall, you know, the water is just flowing over the side of a hill, but then you temporarily would have a dy dl of negative infinity. Okay, so here are some pictures of the shapes as the water is in a different zone. So here, if the slope is mild, meaning less than the critical slope, if the water is in zone 3, the water depth has to be increasing. It'll always be increasing in the direction of flow. Anybody know of a physical feature that causes an M3 profile? Like, go ahead.
Eddy.
An eddy? Maybe. Like, think about like an engineered structure, something that you could put into the channel or something you could build that would cause an M3 profile. So M3 means normally it would be flowing subcritical because, you know, this is a subcritical slope. But now here the water is in the supercritical zone. You know, if your depth is below the critical depth, that means right now the flow is supercritical, and it shouldn't be. So what causes that? An underflow gate, right. All right, an M2 profile. Anybody think of a physical feature that would cause an M2 profile? So the water depth is decreasing in the direction of flow.
Waterfall.
The waterfall. Yep. And what about an M1 profile?
To build up energy to have a another flow.
So upstream of an underflow gate. So an M3 would be downstream of the underflow gate after the water has actually gone under the gate. And M1 would be upstream of it as the water's pooling to gain energy. It could also be any other kind of a choke. For example, a broad-crested weir could cause an M1 profile. So here are some S profiles. Now it's a little bit different when you've got an S1 instead of an M1. You can see that an M1 is gradually becoming steeper in the direction of flow, but an S1 is gradually becoming, you know, the slope is tapering off. And so whatever the feature is upstream rather than downstream that's causing the change. There isn't a C2 profile, and so you won't have the because in a critical profile the normal depth is equal to the critical depth, and so there can only be, you know, the water depth is either above the line or below the line because both of those lines are on top of each other. So that's why there's no C2 profile when the slope itself is critical. And the same thing is true in the case of a horizontal. There isn't a normal depth. If you've got no slope, you can't solve Manning's equation for some depth if the slope is 0. You can have the critical depth just based on the flow rate and based on the channel geometry, but you won't be able to solve for a Manning's depth. And then in an adverse profile, when the water is flowing uphill temporarily, it can be an A3 profile, meaning that it's getting deeper, an A2 meaning it's getting shallower. But again, there's no normal depth for uphill flow. So that's why we only see a single line in both the horizontal and adverse slopes. All right, so an M1 profile could be caused by any kind of an obstruction. This is like a dam of some sort, like a spillway, and the water's going over the spillway at a critical depth. Here's the flow over a drop-off, hydraulic jump. So before the hydraulic jump is gradual flow as you've got supercritical conditions, and it's gradually increasing until it matches the sequent of the normal depth downstream. So those are some things that can cause mild slopes. Here are some features that can cause steep slopes. So here we've got a supercritical slope, a normal depth, and then it has to go through a hydraulic jump to match up with the S1 because it's going to be temporarily, the normal depth should be below the critical depth, but this is going to be forcing the flow depth to be greater than the critical depth, and so it has to go through that hydraulic jump to match it. These are in the book, pictures like this, and so if you have a problem where you're asked to draw, I think you do have a homework, where you're asked to draw, like after a gate, what would the profiles look like? Then it can kind of give you an idea of like the typical shapes of the water surface. Here are some hypothetical situations that could cause an A2 and an A3 slope, or if the slope itself is critical, what could cause a C1 and a C3. This is just another book's way of showing it, and I like this because it's got in the same diagram, it shows you dy dx is positive. So you can use this to help you analyze whether it's an M1, an M2, or an M3. So what you're doing is you're comparing the given depth to the normal versus the critical, and so then that will tell you if the dy dx should be positive or negative, and comparing the normal depth to the critical depth will tell you if it should be a mild slope or a steep slope. And this is what we'll have most of the time, is an M and an S. These other ones are far less common, very unlikely to have a horizontal slope or an adverse slope or critical. Here they are, but they don't happen very frequently. What we've got is a rectangular channel that we're sending 31 cubic meters per second through, and the flow depth at a certain spot is 3.2 meters. Now, at first glance, it looks like maybe the problem is overspecified here, meaning that we could solve Manning's equation and find a depth, and it's not going to equal this flow depth. But remember, Manning's equation is all about uniform flow, and so what's happening here is it's non-uniform flow. And so we can solve for the critical depth and find out what would the depth be if the slope was critical. And we can solve for the normal depth using Manning's equation and find out what would the flow depth be if conditions were uniform. But then this is the actual flow depth. And so the first thing we're going to do after we find the normal depth and the critical depth is try and find out what is the profile criteria and how does this fit in. In other words, where in zone 1, 2, or 3 does our existing depth of 3.2 meters fall? And is the slope mild or steep? And so is this M1, M2, M3, S1, S2, S3, and so on? All right, so just to speed things along, let me show you our normal depth and our critical depth. First of all, the normal depth, we can say, using Manning's equation, 31, I brought the good marker again today. Let's try this red one. 31 cubic meters per second is 8.5 times y sub n. So 8.5 is the channel width. So 8.5 times the normal depth is the area, and that's to the 5/3 power. We put in the n value of the channel here, the roughness coefficient 0.033, and then the wetted perimeter is 8.5 plus 2 times the normal depth, and that's to the 2/3 power. And then we have the slope 0.001 to the 1/2 power. And just put that into our solver and get that the normal depth is 2.717 meters. And then the critical depth, since it's a rectangular channel, it's easy to find the critical depth by knowing the flow per unit width. And so the critical depth will be 31 cubic meters per second divided by the 8.5 meter width channel, and then so that's lowercase q, square it, and it's divided by g, 9.81 meters per second squared, all of that to the 1/3 power. So we have 1.107 meters for our critical depth. So compare the three depths that we know about. Compare the normal depth and the critical and the given. So the given depth is 3.2, the normal depth 2.717, and the critical depth. So the first thing we want to do is find out, is the slope mild or steep? And we do that by comparing the normal and critical depths. So here on this diagram, it's showing the normal depth is the deeper one when you've got mild. Normal depth is greater than critical depth, so that means we have a mild slope. If it were steep, steep is the one where the critical is deeper than the normal. But that's not what we've got in this. The calculations we just did tells us that it's a mild slope, and then the given depth of 3.2 is greater than both of them. So that means it's an M1 profile. So going back to here, the rationale you need to include in a homework assignment or a quiz or an exam, when you're saying what kind of profile it is, it's not just sort of like a 1 in 6 guess. It's you get the right one and you explain the criteria why. So the rationale here is that the given depth is greater than the normal depth, which is greater than the critical depth, so therefore the water surface is an M1 profile. All right, so that's the first part of it. Any questions about that so far? Now, we want to find the water surface slope. We're going to use the process equation to do that. So we can find the slope of the energy grade line and then substitute that into dy dl. And I'm going to pause the recording and give you some time to do that. For the slope of the energy grade line, S sub f, using Manning's equation, this time you're solving for S, and the depth that you're going to put in is the actual 3.2 meter depth. And so it's kind of a little bit different from what we're usually putting into Manning's equation. Ordinarily, in Manning's equation, we're assuming uniform flow, so the water surface slope is parallel to the channel bed slope, which is parallel to the energy grade line slope. But what we're saying is we can find the slope of the energy grade line by putting in the actual water depth of 3.2. So solve for S using Manning's equation, and the S that you'll be solving for with this depth of 3.2 is the slope of the energy grade line. And then you'll also need to solve for the Froude number. And let's see, we don't have the formula for the Froude number there. Here's one. Let's just paste that over. Now we've got it. All right. All right, so that's all we need. So find basically dy dl. Okay, so it's key that we put in the actual flow depth of 3.2 meters when we're solving for the slope of the energy grade line. It's maybe hard to keep it straight because we've got three different depths that we've been talking about. We've been talking about the normal depth, the critical depth, and the actual flow depth. But it's the actual flow depth that gives the slope of the energy grade line. All right, so we get 0.000634 for that. The Froude number, here's our flow rate squared, the top width, which is the same as the bottom width in this case, since it's a rectangular channel, 8.5 meters. G, the cross-sectional area, will just be the flow depth times the width. So our Froude number squared, I leave it in terms of Froude number squared just because that's what you're going to substitute into the process equation. No sense finding the Froude number and then having to square it again. So what we get is the slope of the water surface is a positive number. It's not changing a lot in the direction of flow, 0.000382. So at this particular location, that means that the water depth is increasing in the direction of flow. And hopefully that makes sense. Let's go back to the water surface profile sketches. These typical diagrams say that in zone 1, you see the little drawing here shows that in the direction of flow it's getting deeper. That's what this is meant to convey. And it also says dy dx is positive. So everything lines up as we would expect. It's getting deeper in the direction of flow. Now what if the flow depth was 2? So if the flow depth was 2, then that would put us into a different zone, because what we had done earlier is solve for the critical depth and the normal depth, and so 2 would be between the normal depth and the critical depth. So if it said in the problem statement that the depth was 2, then that would mean that we'd be in zone 2, and if we went through all the calculations again, what we'd expect to see is that dy dl in that case should be negative, because an M2 profile means that the flow is getting shallower in the direction of flow. So that's just the hypothetical to keep in mind. Any questions from the example? All right, so this is the slope at just a single spot of the water as it changes depth. And remember, the challenge that we face is that we don't want to extrapolate too far, assuming a linear profile, when really the water surface is changing gradually. So let me refresh your memory about here. We've got a stream, and the water depth maybe is getting deeper as it approaches some sort of an obstacle, maybe an underflow gate where the water is continuing on. And so if we found the slope at a certain location and we just extend linearly, then the actual depth some distance downstream, if we said here's our delta x, and we just applied the process equation directly, it would underestimate the depth downstream.